Welcome back. Did everyone have a very good lunch? Lunch for everyone. You had a good lunch?
Fantastic.
Great.
Best
I'm
ever.
jealous. Okay, let me begin by attempting to explain the last theorem one more time, to explain it better and more clearly. And then I want to try to discuss the proof. So the situation is this: we have L and we have G, and inside of G we have one of these Levy subgroups. It means a block diagonal subgroup. And we might ask whether every representation of G comes from this transfer operation that we discussed from a representation of L. All of G in representation theory terms described by L. And so this is something that Harishchandra thought about. And the theorem, due to him, is that if, when you take L and you start to conjugate it by elements of G, so now this is a subset inside of G, if this is dense, so if L meets almost every conjugacy class in G, if this happens, by the way, then the complement is very small, has measure 0, is a closed subset, closed algebraic subset of dimension less than a dimension of G, so it has measure 0. If this is the case, and we'll discuss in a moment some examples, then indeed this transfer map, the transfer homomorphism, let's call it the transfer morphism. Let's write it in this fancy way, using a fancy arrow. It's some sort of generalized star homomorphism from the Cstar algebra of G, the convolution algebra of G, to the convolution algebra of L. By the way, I forgot to say it, this has a name. Not in the world of Cstar algebras, but in the world of so-called Schwartz functions, Harishchandra Schwartz functions. This is called the Harishchandra transform. So in the background, it's not explicit here, is some parabolic subgroup. And one usually labels the transform by the parabolic subgroup. But anyway, this thing is injected. And according to elementary Cstar algebra theory, this means that every irreducible representation of G comes from an irreducible representation of L in the sense that we've been discussing. So it's an interesting theorem. You can declare partial victory at this point and say that you know the representations of G because by induction you know the representations of L. It's presumed that L, which has a lower rank, you've already dealt with. Okay. And as for the hypothesis, there's a little lemma or a proposition which says that such an L exists if and only if such an L exists if and only if the centralizer, let's assume G is connected in a compact center, otherwise what I'm about to say is obviously false. Now, such an L exists if and only if the centralizer of T, not in K, but in G, is compact. T being a maximal torus in K. Yes, shit. Non-compact. Get it right. Almost. Okay. And what's going on here is that if you're in this, this is not complicated, by the way. I've made it much more complicated than it really is by making, every time I tell you about it, making a mistake. And, but it's very easy. And the idea is this, that by changing T within its conjugacy class, you can always arrange that there is some one-parameter group to commute with T. If the centralizer is not compact, this is the reason. It contains a one-parameter group of the type we were discussing, for some H in the space we were discussing, non-zero, of course. And in that case, you can take L to be the obvious choice, namely the Levy subgroup associated to H, by the construction, the centralizer that we discussed earlier. So it's not very mysterious what's going on. The theorem is quite impressively difficult, and yeah, I'll try to describe what's going on, but the proposition is not impressively difficult, and the condition is very easy to check in any given case, and I showed you all of the cases, basically. You just check them one at a time, although you can do much better. All right, so let's just look at some examples. So let's look at any complex group, but for example, SLNC. In this case, you can take a tiny, tiny, tiny L. So we could take this particular L, just the diagonal matrices. In G. So it's associated, if it's a Levy subgroup, it has to come from some H, and here if you just choose any H where all of the A's are distinct, you're in business. If this is your H, then the corresponding, the centralizer is exactly, of course, the diagonal matrices. And this is so what are the matrices in G which are conjugate to something in L? Well, among other things, if you had a matrix in G, all of whose eigenvalues were distinct. If it had n distinct eigenvalues, then it would have to be diagonalizable by a theorem in linear algebra. And generically, every matrix has n distinct eigenvalues, so it's over. If you look at the matrices with n distinct eigenvalues, that's a huge open set in G, and it's contained, yeah, in this thing, in this saturation of L, so it's over. So the hypotheses are satisfied here. But you can also do this for SLNR, not all the time, but if n is sufficiently big, bigger than 2, and the L, the sort of minimal L you could take, looks like this. There's more than one L which will do the job, but for example, the L which consists of 2 by 2 blocks like this, and at the end, it'll either be a 2 by 2 or a 1 by 1 block, depending on the parity of n. This will do the job. If you have an SLNR matrix, a matrix over the reals, you can't diagonalize it even generically because it may have not any real eigenvalues. And so it cannot be diagonalized inside of SLNR. But it can certainly be block diagonalized into 2 by 2 blocks in which you join together the complex conjugate pairs of imaginary eigenvalues so as to obtain, complex eigenvalues so to obtain real matrices. So you can always block diagonalize, as you know, over the reals not any, but almost any n by n matrix, an open set of matrices. Okay, so you're in business. The set of matrices in SLNR, which have n distinct complex eigenvalues, is contained in the saturation of this particular L. So in both of these cases, in particular, there are none of these fancy compact representations, no discrete series representations. Because those would be representations which are in the kernel of this map, and this map won't have any kernel in this particular case. All right, while we're at it, just for fun, I want to do this. Yeah, just a little remark. I said that sometimes you can work out in a fairly easy way when these parabolically induced, these transferred representations are irreducible. And let's just look at a small example to see what's going on. All of the big examples, as far as the general statements go, all of the big examples are treated in exactly the same way. It's just more complicated. And then there are very subtle situations in which you want to understand exactly what happens, not more or less, which is what I'm going to describe here. Suppose G is SL2R or SL2C. These two cases are slightly different from one another, and let's try and understand both at the same time. And to go back to old-fashioned notation, let's imagine parabolically inducing some representation phi. So pi is this group of upper triangular matrices, and phi is some character on the diagonal matrices. It's an irreducible representation of the abelian group, which is the diagonal matrices, so it's just a character like this. So remember that the Hilbert space just consists of functions on G into the representation space of phi. Well, in this particular case, we're just talking about functions. And they satisfy some covariance properties. So if you translate on the right by something in L and something in N, what happens as far as N is concerned is nothing at all. And as far as L is concerned, this is what happens. The action of phi is brought into play. And then there's a correction term, which we discussed, and then there's phi. This is the representation space. And the action of G is by left translation. So it's a representation. And there's an inner product, which is, we'll do the norm squared, is given just by integrating not over G, but over K. Like that. So that's how you build this transfer operation. When you unpack all of the details and see what the transferred representation really is, this is what it comes down to. This particular Hilbert space, which has a left translation action of G, with this particular, as it happens, unitary norm. It's not obvious that it's a unitary norm, but it is, thanks to this funny fact here. This is some homomorphism. Delta is some homomorphism from from L into the positive real numbers. And so let's look at this from another point of view, let's do the following thing. Let's restrict to this subgroup, which is basically the transpose of n, the lower triangular unipotent subgroup, and see what sort of space of functions we get. Well, if you have a function in this space, its behavior, so to speak, as far as L and N is concerned, is prescribed by this formula. And if you take this subgroup here, which is the opposite unipotent subgroup, and multiply it by L, and then multiply it by N, you get no longer a subgroup, N bar L, N is no longer a subgroup, but it's a dense open set. And so the functions are completely determined by their restriction. And if you want to get a unit, I want to obtain a unitary isomorphism to just L2 of this group. And for that purpose, I need to adjust by some Radon-Nikodym factor. And I forgot to work out exactly what it is for SL2C, but for SL2R, what you're supposed to do is just multiply by the function which sends this matrix to 1 over 1 plus x squared. It's some explicit thing. This comes from the Cayley transform. These functions here, if you think about it, should naturally be thought of as functions or sections of some line bundle on RP1. And this is a line, and RP1 is a circle, and there's a Cayley transform from a circle to a line, and the derivative of the Cayley transform is that thing there. Oh. These things being as they are, we're trying to get a Hilbert space isomorphism. I guess it should be a square root there. Once you've done all of that, you get some unitary isomorphism from this space here, which looks a little complicated, to L2 of R. That's better. Let's see what's going on. That's the good news. You can see what the Hilbert space is. But the bad news is if you want to understand what the representation of G is in this gauge, in this picture, it's really terrible. However, not all of it is terrible. In this picture, in this L2R picture, N, the subgroup, I didn't give it a name. And this, let's call it N minus, the lower triangle. Oh, and if you do the thing in the complex case, of course you get SL2. You get L2C like that. And this N minus group, which is just a copy of the group R, or C, depending on the case, just acts by translation. And it's a little easier to see what's going on by taking the Fourier transform. So in momentum space, so to speak. This group acts by multiplication.
So what's N minus?
N minus is the lower, is this group up here?
Oh, yeah, sorry.
The reason I tell you that is that any intertwiner, any map from this representation space to itself, bounded operator, which commutes with the entire G action, of course, has to in particular commute with the N minus action. And what you see is that this thing here has to be, well, in Fourier space, let's go back, maybe back to L2R space, it has to be a convolution operator. It's hard to think about convolution operators. But back in the Fourier space, momentum space, if you like, it's a multiplication operator. That's the reason I mentioned the Fourier transform here. So the only operators which commute with the multiplication operators associated to all characters of n bar, or characters of R, are themselves multiplication operators. And so the only possible intertwiners are given by, in Fourier space, multiplication operators. There aren't that many possibilities. Of course, there's still a lot, but we've only used the n minus action. But the diagonal group L acts by dilations in either of these representations. So you can take your pick in let's say, configuration or momentum space, or I guess I'll just continue using the same language here. That's because the Fourier transform of the dilation is just another dilation. So, there's a subtle point which I almost forgot. I almost reached a contradiction in my own mind. What you're dilating by is the square of, when you do the calculation, the 1-1 entry of any matrix in this diagonal group. So you do the calculation, that's the way it works out. So any intertwiner, let's say viewed in Fourier space as a multiplication operator, has to be multiplication by a function which is invariant under translations. It's multiplication by a function invariant under not translations, that's not what I meant to say, but dilations. By all squares. 1 squared, 2 squared, minus 1 squared, square root of minus 1 squared, you name it. Okay. So in the complex case, this function must be constant. The constant functions are the only functions which are invariant under arbitrary dilations by squares. In the real case, the function must be constant on R plus and R minus, but separately. So the space of all intertwiners in the case of SL2R is at most two-dimensional, and the space of intertwiners in the case of SL2C is at most one-dimensional. And so according to Schur's lemma, in the SL2C case, the representation is irreducible. And in the SL2R case, it decomposes into at most 2 bits. It's just an upper bound that we gave, because of all of the G action which exists here, we only used the action of L and then minus. And so we didn't really investigate the full story, but we know for sure that the intertwining algebra is at most two-dimensional, and that's what you only reach, 2 dimensions you only reach in the real case. Here it's one-dimensional, so in the complex case, the representation is always irreducible. And the argument is exactly the same for SL3 and SL4 and SL5, it's just a little bit more complicated to state the details. So this is all worked out by, this is ancient history. This argument is due to Gelfand and Naimak. So what actually happens in the real case is that this upper bound of 2 is realized in only one example, and in all of the other examples, the representation actually is irreducible. there is one example to show that this is as sharp as you can get for a completely general statement. And so it's exactly the same for SLNR, as I say, or for any SLNC, any complex group at all. If you have a complex group, every representation which is irreducible and tempered is exactly the representation you get by parabolically inducing some character. Right? It's the obvious generalization to, let's say, n by n matrices of this formula here. And these are all irreducible, and there are no other representations thanks to the theorem of Harish-Chandra, the one that's up there. So it's we've almost completely understood what the representation theory, the tempered representation theory of complex groups is like. The only thing we didn't understand is when is it that two different characters, two different representations of L give rise to the same representation of G. We didn't discuss that, and that's a problem for another day. Apart from that, it's over. We've dealt with SLNC, as long as we can deal with this thing here. Yeah. Okay, so, there you go. Now, let's try to tackle this theorem of Harish-Chandra, which is, the theorem that's up there. And in order to get acquainted with this, let's consider this strange object, this star homomorphism. And in order to get the idea of what's going on, you don't have to worry about Hilbert modules and so on. Maybe I'll just say more simply. The representation of G as bounded operators, we had an argument to say that representation really was as through bounded operators, of the Cstar algebra on this space. And so now you can calculate. So each, let's just take to begin with a function which is smooth and compactly supported. These are dense inside of here. So there's a formula for how you take a representation of a group and make a representation of the algebra. It's very easy. And if you apply the formula in this case, here's what you get. What you get is an integral operator. So an operator like this, there's some, well, we had a name for it, lambda G mod n of f. And it takes a function h to, let's maybe write it this way, take a function h of y, and now you get some function, let's say of x, we'll use a different letter. And there's some kernel here, integral kernel. So here's a function of x, maybe I'll do it this way. H goes to the function which does this. This is a recipe describing, it would describe the right thing if I remember to include h. And now I just have to tell you what this kernel is. And here's the formula. So k on a couple of cosets, like this. And now I'm going to write down a function of two cosets, which is obtained out of the original f. And I just integrate over gf of g1 times n times g2 inverse d. So that's how you convert an element of this fellow, for example, an element of this generating subalgebra, into an operator. Here's what it is. And as we analyze this theorem, as we try to prove this theorem, we're going to have to confront a lot of integrals like this, which involve integration over n. And you can start to worry as you start to write down formulas whether they really make sense, because here we're just making an integral out of a function. Remember, we started off with a function which is compactly supported on G. And it's, if you think about it for less than a fraction of a second, you'll see that this integral is the integral of a smooth and compactly supported function. So this makes perfect sense. You don't have to worry about the meaning of this integral. But we want to apply this formula to some hypothetical element in here in the C-star algebra, which maps to the zero operator here, and then show that that hypothetical element must be the zero element of this C-star algebra. And so we want to be able to apply this formula not to a nice smooth and compactly supported f. There may be no smooth and compactly supported f's which go to zero here, even if there's a kernel of this map. We want to apply it to a more general such function, and now you have to worry about the meaning of the integral and so on, and this is the source of all sorts of problems. But fortunately, the C-star algebraists have invented some technology about this. So let me just say we shall need to work with such integrals, like the ones just above, for much more general f. And that's a problem. And there's another problem which has the same flavor. It's a sort of analytic problem. And we might as well worry about both of them at once. So more issues of the same sort. I want to work with a linear functional, as people often do in functional analysis. They work indirectly with linear functionals on this space. It's very easy what this is. The G trace of f is just f of the identity. And it has some useful properties. The most important one is that it really is a trace. And we're going to want to work with this not for f, which is a smooth and compactly supported function, but for a general f, which lies in the C-star algebra of G, or an almost general f. And it's a problem to worry about the meaning of the value. It's a different sort of problem now. Now we want to evaluate a function at a point. It doesn't seem like such a serious issue until you realize that inside of the reduced C-star algebra, it's not just the algebra of smooth and compactly supported functions. L1 of G sits inside of the reduced C-star algebra. L1 of G embeds into the C-star algebra. The algebra of under convolution of L1 functions embeds in the C-star algebra. And now there's an issue, because if you have an integrable, measurable function on a group, it doesn't make sense to evaluate it at a point. What are you going to do? You're not allowed to evaluate functions in L1 at individual points. You're allowed to change them on sets of measure 0. So it's a problem, a different sort of problem, but a problem. And we might as well solve both at once. The reason we're interested in this trace is that if you apply it to the adjoint of a function times a function like this, then what you get is the L2 norm squared of f. So this linear functional secretly remembers the Hilbert space. And in fact, the C-star algebra norm of f, which is what we're super interested in, we want to show that every element in the kernel of this map has C-star algebra norm 0. That's what it means for it to be injective. You can write this in the following way. This is the supremum of all quantities like this, the G trace of H star, F star, F, H. So everything here should be in, let's say, CC infinity, so we don't have to worry about what it means. And then, oh, there's a side condition. Just this one. So you can entirely capture the Cstar algebra norm, at least theoretically, in principle, by this formula. It's not a very useful formula, because it's a supremum. But if you know the G-trace, then you're in business, and in particular, if the G-trace of F star F is 0, then that implies that F is 0. In fact, it's exactly the same. Let me write it this way, which of course makes it F is 0. And we're going to argue that if we have an element in the kernel of this map, then indeed the G-trace of F star F has to be 0, and therefore F has to be 0. But in order to successfully carry out the full argument, we'll need to apply this not just to compactly supported smooth functions, but to all functions, so that we're following the law, we're not cheating. And okay, so it's an issue. Let's see if we can keep this for a little while. And so there's a trick in Cstar algebras to get around these technical problems. We want to build some space of functions which is big enough so that it suffices to consider those functions, and yet small enough so that all of these objects, the various traces and so on that I've written down, actually make sense, and the integrals that we had up here. We want to be able to legally manipulate such integrals for functions which are much more general than smooth and compactly supported. And we want to legally evaluate such functions at 0 in much more general situations than when we're dealing with smooth functions, in order to be able to prove this theorem. So there's a little Cstar algebra trick. So let's start with the space of functions that we're most confident with. And let's just build a new norm on this old space. Maybe we'll call it the triple norm like this. And what I'm going to write after the equals sign is everything I could conceivably be interested in. Well, I could be interested in the Cstar algebra norm. Maybe at some point I'll want to think of F as an element in L2 of G. Okay, stick in the L2 of G norm. And maybe, in fact, what I'll want to do is take F and integrate it over N to make it a function. Let's call it F sub N in L2 of G mod N. So what F sub N means is I integrate over N cosets in order to get a function which is in G mod, L2 of G mod N. It's invariant under right multiplication by N. And what else? Well, maybe I'll be interested in the trace of F. Actually, you're not allowed to just do anything. I'll explain what you're supposed to do in just a moment. And this naked term here is not such a good term. But for example, this would be a good term. This, using the Cstar algebra norm here. And it's strictly speaking, so this is okay, but it would be a little bit better to take F and multiply it. Let's do the same thing, make it supremum. Multiply it by any H, and then average over N like that. again, the same sort of condition on H. It should be a smooth function just for convenience, just to make sure everything makes sense. Then we'll take the Cstar algebra norm. Okay. And et cetera. There's a law telling you what the et cetera should mean, what the conditions really are. Let me describe that.
For star, is it trace of G, trace of F? Star F.
S, G of F.
So,
1, 2, 3, 4. This one?
yes.
Yeah. Oh, I mean, it's not quite a. Do that first of all. But yeah, you could do this. This supremum includes this number as it happens. So this number, this is not a good number by itself. The only reason I'm allowed to put it here is that this term here is bigger than it. This is a legitimate term. This is a legitimate term, which is bigger than this thing, and so on and so forth. And now let me tell you what the law is, which is telling me what I can put. So what I'm going to do is I'm going to take CC infinity of G, and I'm going to take the norm completion with respect to this norm. Okay? So the good terms on the right are norms. They should be norms. Vector space norms. But they should also have this condition that strictly speaking, what I'm about to write down you only need on one side, but it's more elegant to deal with both sides at once. Let's call them norms of A or something. So they're, well, I don't know what, they're sort of multiplicative norms relative to the norm of the Cstar algebra of G. So now let's complete the algebra. This is infinity.
So, sorry, this whole expression is a norm.
And the whole, it's just a sum of norms, and not only is it a norm, but it's sub-multiplicative, thanks to this relationship here. So it's, when you complete, you suddenly get a Banach algebra.
It's a good exercise to prove that.
Yeah.
It's sub-multiplicative.
Yeah, it's, well, here, 1, 2, 3, 4, 5, there are 6 terms here. So if you multiply this norm by another such norm, you'll get 36 terms. Heavens above, 36 terms should be enough to bound anything. So it must surely be the case that the norm of f times h is less than or equal to
That's
the...
not counting the et cetera.
And the et cetera, yeah. So, yeah, when you think about the Banach algebra law, the submultiplicativity, the more terms you add, the better off you should be. And indeed, you're in a very good situation. Here's how good, you might ask. Well, here's how good. This is, so we get a Banach algebra which embeds, not as a closed subalgebra, embeds in the reduced Cstar algebra of G. Write this down here. It's sort of obvious from the definition that the trace is defined on this Banach algebra. In fact, before I do that, let me just point out, this thing is actually a two-sided ideal. Not closed, of course. We can test for vanishing not by checking each of these norms, oh, that would be horrible, but just by looking at, of course the trace extends by continuity to it, because we stuck it in there, and the trace is 0 if and only if f is 0. And let's go this way, sorry. And the Cstar algebra is compatible with the functional calculus that people have in the world of Cstar algebras, closed under the so-called C infinity functional calculus. So remember that if you're in a Cstar algebra, and you have a self-adjoint element, and if you have a function, let's say a continuous function on the line, you can do better than that, of course, then there's a way of defining f of a in, back in the Cstar algebra. Let's call it a or something. In such a way that if f was a polynomial, it would be the obvious polynomial in A, and the map should be, is continuous in F with the topology of uniform convergence on compact sets. So that's the functional calculus, and it's a fundamental fact about Cstar algebras that there is such a continuous algebra homomorphism from functions on R to elements of A. And what I'm saying when I say closed under the C infinity functional calculus is that if A is in this subalgebra, and if f is a smooth function, then f of A is in the subalgebra too. And that tells us that our subalgebra, our dense ideal, intersected with any closed two-sided ideal, carried away there. It's still dense in that ideal. So going back to our homomorphism that we're trying to show, the one in the theorem up here, that we're trying to show is one-to-one. If it's not one-to-one, then it has a non-zero kernel, which is an ideal. And inside of that ideal is something in this dense subalgebra. And on that dense subalgebra, you're allowed to take the trace. And you're allowed to integrate over n cosets. You can do whatever you like, because we stuck it all in the norm here. Okay, so there's a little bit of analytical background to help us along. And now, let me think. I'm going to, let's do the following thing. Let's soldier on for a few minutes so I can get to the gist of Harishchandra's argument, and then we'll take a little break, and then we'll resume with a different subject afterwards. So 10 more minutes of hard work, and then cocktails for 10 minutes, and then some more mathematics. Yeah, question, please.
I got lost. So could you just say again what this two-sided ideal is?
It's the completion of the smooth compactly supported functions in this norm. Thanks to the fact that we threw in the Cstar algebra norm at the beginning, this embeds, maps continuously into the reduced Cstar algebra. In fact, that map is one-to-one. That's the first thing. Oh, that's it. So the image is the subalgebra I'm talking about.
The image of the compactly supported smooth function.
Completed with respect to this norm.
Yeah. And the Banach algebra itself is bigger than that.
The Banach algebra is precisely the completion. We can think of it as an abstract Banach algebra, whose elements are limits of Cauchy sequences and so on. Or we can realize it as a dense subalgebra of the reduced Cstar algebra of G. It's a little theorem that the natural continuous map into the reduced Cstar algebra is one-to-one, but it is. And so we constructed in this way a dense subalgebra, which has all of these nice properties. It's an ideal, the trace is defined on it, blah, 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 blah. And if you intersect it with any ideal in the Cstar algebra, you still get something, dense ideal.
Okay, so how is this ideal different from this completion?
Well, it's just, it's abstractly isomorphic as an abstract algebra to the completion. It's just embedded inside the Cstar algebra.
It's an ideal in the reduced Cstar
Yeah.
algebra of G.
Yeah.
Sorry.
Okay.
Apologies. You said this 3 times, so I finally got
Great.
it.
You said it once, so that.
Sorry. Thank you.
No problem. Other questions? He's sitting the closest, so he understands the best what's happening for the people at the back. No questions?
But you only need to repeat 3 times.
All right, so 10 more minutes and then we take a holiday, 10-minute holiday. Tsuyoshi will serve martinis and then we shall continue. You have 10 minutes to find the martini.
I'm sure there is a vending machine.
It's probably only funny if you're not Japanese. Okay. Right. So I tell you these things to suggest to you that there is a framework in which you can carry out the following calculations. Now I'm going to do calculations like I would if I was a physicist. You know, I worry about reading the theorem its rights afterwards. I worry about the details later. But if you want to worry about the details, this is how you do it. But there's only 10 minutes, so we don't worry about the details. I sketched to you now this incredible argument of Harishchandra to prove this theorem. So the only role of Cstar algebras here is to provide a sort of simple theoretical framework to carry out these calculations. By now in Cstar algebra theory, we are used to doing this. Dense subalgebras which are closed under some calculus. This is a standard part of Cstar algebra theory. And it was worked out long after Harishchandra conceived of this argument. First thing to note is that if f is in the kernel of the map that's up there, then according to our calculation, of what the map really is, we can say that all of these averages over n, not just of f, but all of the translates of f, they're all 0. And the integral makes sense because we threw it in the norm to make sure it made sense. So what we're going to do is we're going to obtain a formula for f at the identity for this trace in terms of these quantities, and then we'll be done, because if these are all 0, the trace has to be 0, but then f has to be 0 by this. Okay, and I was just about to say something else, and I forgot. We'll worry about whatever 2 was, we'll worry about it later. So for the sake of argument, let me suppose that f is a little function, a function which is supported in a little neighborhood around the identity element of G. Okay? And it's not legal to assume this and this at the same time. It's not the case that things in the kernel can be approximated by functions which have this property. So there is we have to fix something later. This is too strong of an assumption, but let's assume it anyway to see what's going on. And we want to get a formula for the trace, f of e. Okay? Well, the first thing we're going to say is that this is f of 0, where the following holds. Big F is just little f composed with the exponential map. So big F is a map on the Lie algebra. And of course, it's like little f, it's supported near, well, not the identity, but near 0. And now we invoke a well-known principle from Fourier theory, finally. So we have to use Plancherel somewhere. So what we'll invoke is that the value at 0 is exactly Plancherel's formula. It's the integral of x dx over the entire Lie algebra of G. have to get n into the picture, integrals like that into the picture, and we have to get it would be a good idea to get the hypotheses into the picture too. That would be helpful to get somewhere. So here's what we're going to do. We're going to use, before I do that, for the sake of the argument, let me assume that f is invariant under conjugations by elements in K. By averaging, I can always take an element which is not necessarily invariant under K and make it invariant under K. So this is not a big deal, but it simplifies matters quite a bit. Now going back to this integral here, I want to saturate G in the following way. Oopsie. Let me do it like this. Here's the Lie algebra of L. I'm not quite sure how to draw fractor L. There's going to be some Radon-Nikodym, some Jacobian factor here, which is going to be a polynomial. In L. It's a Jacobian which comes in the change of variables formula. And then what I'm going to put is the integral over K, the integral over n of big F hat of K inverse n inverse L and K. This is just Weil's formula. Weil says you can always write down such an integration formula, and I'm using the fact here that G is K times N times L. Not disjointly necessarily, but almost. Do it at least one more step to give us something to enjoy. Well, let's do some easy step first over there, and then we'll come back over here. Sorry, one more step over here. You can forget about the integral over K, because I was assuming that F was conjugation invariant, so this is the integral over the Lie algebra of L. There's some function here, and then there's just an integral over n of F hat of n inverse x n. Again, dx. That's a little bit encouraging because after all, there's an integral over n here, and there's an integral over n up there. Now, suppose I take, I write n x n, like add n of x. X belongs to the Lie algebra of L, and L is a subgroup of L times n. And, yes, Jacek.
Do we not get a constant out of this integration by K?
Oh, yeah, set all constants equal to 1. Yeah.
Oh, I see. Oh, you did say that the volume of K is...
I did, but I'm also invoking Plancherel's formula, and I didn't tell you so much about what the details are, what the Haar measures are.
So whatever constant we get is 1.
Yep. That will lead, the final formula that I get will have a constant in it, which one has to calculate by remembering all of the constants that went through. And let me just say one more thing, and then it's time for cocktails. So this is in the Lie algebra. Of this parabolic subgroup. In fact, this thing is equal to x modulo n. because n is normal in Ln. So nx, n inverse, is equal to some element, let's call it nu, of nx plus x. And this nu is now a map from n times L into L. Sorry, the wrong type of L. I've done it this way. We should have been talking about the Lie algebras 2 here. So this is actually a map from the group times the Lie algebra of L to the Lie algebra of n. And the final wonderful fact for prior to cocktails is this, that if you're integrating, as we are over here, over n, I'm sorry, it looks like it was n inverse xn there, and here it's n x n inverse, so that's a typo. It should be the same. But let's, it doesn't, okay, I'm sorry for that small typo. I'll continue with this. I'll continue with this quantity here. This is equal to some factor, what did I call the previous one, alpha, let's call this beta, which turns out only to depend on L, again by this Hermann-Weyl trick, times the integral of f of x plus y dy, and now we're integrating over the Lie algebra. And this sort of integral, that's the wrong sort of f. Definitely time for a cocktail. This sort of integral now looks rather like the sort of integral we have up here. It's very clever. So we're trying to evaluate, get a formula for f of e, and blah, 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 blah. We go through some various steps. And what we end up with is a formula which will involve integrals over cosets of the Lie algebra here. Here upstairs, the hypothesis involves cosets of the Lie group. Not much difference between the Lie group and the Lie algebra if your group is unipotent, because the exponential map is a diffeomorphism. This quantity here, thanks to our hypotheses up there, this quantity is identically zero. If we can put everything together, then we'll have been able to express f of e, the trace, in terms of something which is identically zero, and that will tell us that the trace is identically zero, and therefore that the map has to be injective, under the hypothesis, that is, that f is in the kernel. So we're on our way to connecting together a bunch of really interesting ideas, and so one crucial step is the idea of Plancherel, the formula of Plancherel, right here. And the other crucial step is this brilliant observation of Hershchandra, that conjugation and integration over cosets are basically the same thing. There's some other non-zero polynomial. This is some polynomial, in fact, invariant polynomial in L, not quite the same as that polynomial there. It's beginning to look rather good, and now we'll take a little break and continue in 10 minutes. We shall resume at 3:15. So
we have 10 minutes break, and we start again from 3:15 lecture.
thank you very much. I added in red just a little hat, two little hats, like you see, Fourier transform hats. What I wrote before is true, but if you think about the continuity of the argument, here we're discussing f hat, and f hat, and f hat, and f hat, f hat. It should have been f hat, not f. And so the story so far is we have a formula for this in terms of integrals which look like this. And I said at the end, maybe after the end of the lecture, I said we're almost there because this quantity is known to be 0 by hypothesis. That's what's written up there. But that's not quite right because of the hat. We have to get rid of the hat so far. But there's a very clever trick to get rid of the hat, which is the second application of the Plancherel formula. But before we go on, maybe it's worthwhile just making a little example of this thing. Because then maybe you'll believe that some crazy change of variables formula is possible. So, needless to say, we'll look at the simplest possible example, SL2. X is supposed to be in the Lie algebra of the diagonal matrices. So in other words, X is going to look like this. What should we call it? Little x minus little x. And we are supposed to be conjugating by some n matrix. Maybe we'll put a y there. And the way we did it was n. So, of course, it's just a question of matrix multiplication at this point. But if you do it, I believe you'll get an x there and a minus x there, and 2xy. Oh, I'm sorry, no, I was about to say something stupid, so let me not say it. Okay, so when you change variables and do this integral, instead of this integral, this function beta of x that's being discussed is just, in this particular case, 2x. There's a rescaling of this corner variable here by a factor of 2x. So that's the sort of thing that happens. Beta is always some polynomial. Here it's just 2x. Okay, and now to continue. So we're integrating over a vector space here, the Lie algebra of n. Fourier transform. So the Lie algebra of n, maybe it's worth pointing out here, is just a vector subspace of G, and what we're integrating is the Fourier transform over some affine subspace modeled on this linear space, like this. So if we were integrating over all of G, this would be the integral of the Fourier transform over all of G, and we would get back f of 0, because that's the way the Fourier transform works. If you integrate the Fourier transform over all of phase space, you get the value of the function at 0. This is the theorem of Parseval. But here we're integrating not over all of G, we're integrating over a subspace of G, just n. But there's a formula for that too. Also, well, maybe this is due to Schwartz, I don't know. But anyway, it's some elementary thing. When you calculate this integral, here's what you get. You get an integral now over the orthogonal complement, which I need to discuss a little bit, of the following thing. So what I'm going to do is just basically write the Fourier transform here. So I want to take the pairing of, let me just get the letters right. W or something, so x. So what's going on here first of all, in order to define the inner product, in order to define the Fourier transform on functions on a vector space, you have to equip that vector space with a bilinear form. And you can use any bilinear form in the whole world as long as it's non-degenerate. And the one that's good for us is the trace of xy. So that's a non-degenerate bilinear form on our Lie algebra G. And if you take the orthogonal complement in this bilinear form, so the set of all matrices with the property that they're inner product in this sense, with every n matrix is 0, what you get back is n. Well, actually, you get L plus n. So this converts an integral of f hat over n to an integral of some Fourier integral over L plus n. And what actually emerges, therefore, is something like this. Down here. Another clever trick due to Harris-Chandra. And if you take the inner product in the sense of any n matrix with any other n matrix, you take the trace of the product of two strictly upper triangular matrices, of course you get 0. There's nothing on the, going to be nothing on the diagonal. And so what you find here is that you can write this integral as a combination of two integrals, an integral over L and an integral over n. I'm breaking up this integral using this decomposition. And I'll get a term which is e to the I. It's a good letter. I don't know why. It's the variable here. It's x. It's an x here. This one. Now, the integral, oops, I really wanted to do it like this. I'm going to write down the same thing, just putting the integral in a different place. It's correct, but this got a little lonely out there. So I'm continuing from down there. And what this is, it's a Fourier transform of a certain function of x1, which is an element of L. But it's the Fourier transform no longer over G, but using the vector space G. It's the Fourier transform using the vector subspace L. There are two Fourier transforms in this story. We started with Fourier transform on G, vector space G, and now we're going to use the Fourier transform on the vector space L. So let's call it something a little bit different. So what's going on here is we're taking a certain function of x1 given by this formula, and we're taking a Fourier transform of it in a slightly different way, and we're evaluating the whole thing at x. So what's going on here is that h of x1 is just the integral over n of f of x1 plus y dy. That's the definition of the function h. And finally, this is the Fourier transform. Now it's a function not on G anymore, but a function on vector subspace. G has disappeared, and we have some formula just involving that. Now this is this, however, is a good integral. Remember, big F is probably still up here. It was just little f composed with the exponential. So you can actually rewrite this in terms of little f. This is just little f of x of x1. And now we're integrating. And that thing we know to be 0 if we're in this hypothetical world where we have an integral function in the kernel which is also compactly supported. It doesn't ever actually happen. But if you had an imaginary function which satisfied that it was in the kernel and supported the identity, then we would know that this thing is identically 0, and therefore this thing is identically 0, and therefore this thing is identically 0, and therefore f of the identity is identically 0, and therefore f basically is the 0 function, because you can repeat this argument with not f, but with f star f, and then you get the norm of f squared is equal to 0. So it's very, very clever. And we're almost there. I think. Putting everything together, we get a formula like this, integrating over L. There's some alpha of x divided by beta of x. This quotient turns out also to be a polynomial in x. In other words, beta of x is always a factor of alpha of x. And incidentally, it's not just any polynomial, it's invariant under conjugation. Group. I'm integrating over the algebra. And so what we have here is this L Fourier transform of, what do I call it? So, in order to calculate f of the identity, first of all, I form this average over n. Secondly, I take its Fourier transform. Thirdly, I multiply by a polynomial. And fourthly, I take the inverse Fourier transform. Let's just look at steps 2, 3, and 4. I have a function. I take its Fourier transform. Then I multiply by a polynomial. And then I take the inverse Fourier transform. If I do that, it's the same thing as taking the function and differentiating it with respect to some differential operator. Multiplying the Fourier transform by a polynomial is the same thing as differentiating the original function by some differential operator, depending on the polynomial, of course. So another way of writing this is the following thing. We take the function h, and now I can think of it, maybe I should call it little h, and apply some differential operator to it, and now evaluate this the identity, where h of L, this function on L, is just the integral of h of L n, excuse me, f. And d is some invariant differential operator on and this is a formula which I've proved for any function f which is supported near the identity. But if I have a function f which is 0 in the neighborhood of the identity, it's obvious that, sorry, on conjugate classes, it's obvious that both sides are going to be 0, and therefore I can extend from functions near 0, functions supported near 0, I should have said on a G invariant neighborhood of the identity, I can extend from those to arbitrary functions. So this is true. We can extend just by linearity, if you like, to all functions f, not just those supported on a small, let's say G. I should have said G invariant, and I'll say because I can take, if I have any function, I can write it as a function supported on a small G, conjugation G invariant neighborhood of the identity, plus another function which is 0 near the identity. And obviously I'll get 0 here for that other function, but I'll also get 0 here. And so this must be true for all functions. This is a universal formula, and so I can apply it now for any f, including a hypothetical f, which is in the kernel. And when I do that, I see that there's a formula for the trace of any function in the kernel in terms of integrals like this, and these are all 0 for something in the kernel. And finally, we're done. This is the argument for Paris chain. It's quite a production, and all right, we're proving something rather substantial about representations at this point. For example, we completely determined all of the representations of SLNC, all the attempted representations of SLNC, modulus and question of equivalences using this theorem. So it's not a trivial theorem, and we expect to have to use some Fourier theory, because after all, our group could have been an abelian group, and then it would be all about Fourier. And this is the ingenious way in which the Fourier transform is extended to the non-commutative realm. Thanks to Harris-Chen. So this is the algebra. To make a legitimate argument, you have to combine the algebra with some analysis. You have to obey the law and make sure that all integrals converge and so on. And for that, the techniques that I mentioned can be applied. All right. Finally, the last topic for the day. Are the groups for which this argument does not apply.
Is that operator D related to Durand operator? It's just some differential operator.
This for SLNC, for example, if you wanted to do this in the example I was describing, this operator would have order, roughly speaking, n squared. These polynomials that I'm writing down, this quotient of polynomials for SLNC, has order roughly n squared. So, yes, there's a Dirac operator lurking around. It's not exactly.
It's not that this is not it.
Well, maybe I should say, not that I'm aware of. I don't know the relationship between in this context, the Dirac operator and that differential operator. So sometimes you don't have to worry about classifying discrete series because there are none, and we just discussed that. But sometimes there are. For example, SL2R has discrete series. And we had a long list in the morning of groups, and most of them did have discrete series. And for all of the groups where there was a yes, there were discrete series, for all of those groups, there is no L. There is no L. And everything that I said is not immediately relevant. So now we have to go back and think about that. And one of the things we can say is that if they exist, then centralize it, and by small additional calculation, normalize it. So let's fix the maximal compact. Let's fix the maximal compact subgroup K, and inside of it, the maximal torus T. And this centralizer in G. So we're in this sort of situation. For example, the situation of SL2R. If you look at the SO2 subgroup in SL2R, there is nothing in SL2R which normalizes the circle subgroup except the things that are already in SL2. There's nothing in SL2R which normalizes SO2 except the things that are already in SO2. So this normalizer, let alone the centralizer, they're both just SO2. Right. And so we can play this game again, the usual game. This map is, if we were attempting to study this map in a situation where T had some substantial normalizer or indeed centralizer, this map would be sort of degenerate because there would be many cosets here which commuted with T, and this map would not be onto a very large subset of G. If we are not in this situation, if the centralizer is not compact, then the image of this map has lower dimension than G. It has measure 0, and there's nothing to talk about here. But here, the map has an image which has positive measure. The image is not open, but it includes a very large open subset. And so when we're attempting to understand these formulas for integration over G, we cannot disregard this part of the story. So it's natural to expect integrals like what I'm about to write down contribute in some slightly complicated way, like the way we've been discussing. And so it's natural to expect that these integrals have something to do with that part of the Cstar algebra which is not seen inside of the Cstar algebra above. And so there's a second theorem, Irreducible. Very much inspired by Weil's theorem, to get back to compact groups. I'm not going to go through the proof of this, but what I'm going to do is suggest a different approach to this. I don't actually have the thing looked at, and there'll be a conjecture at the end, and which will involve Dirac operators. So finally, at the end, there will be Dirac operators. But first, some Parrish-Chandra stuff. Let's try to calculate the integral over that part of G, which is conjugate to elements of K. So this is the union of all of the compact subgroups inside of G. This is the image of this map, which has positive measure. Suppose I have a function and I want to integrate it over this space. We maybe have some expectations, some hope, thanks to Hermann Weil, thanks to this argument of Parrish-Chandra, that it's relevant and important to understand such an integral. And, well, you can use Weil's technique. To write this as an integral over T of some quantity, box of T, some Jacobian times an integral over G mod T. And actually, this situation is very much like the situation studied originally by Hermann Weil. I'm going to write down a formula which is very similar to the sorts of formulas that we've seen up here. minus the final step. So this is the first half of Harishchandra's approach to the discrete series. There's a second half to this. It doesn't tell you everything. It just tells you a great deal. And I'll state it in our terms. What I want to study are those elements in the Cstar algebra of G, those functions on G, if you like, which are not seen in any of these under any of these transport homomorphisms. So the intersection, the kernels of all of these maps. In the previous lecture, I called this the basic ideal of this Cstar. And this is the ideal which is made up out of matrix coefficient functions of discrete series representations. Now I'm going to apply the trace to this element. And in order to apply the trace, it's a good idea to be in our subalgebra where the trace is defined. But that's okay. Our subalgebra is intersected with this ideal, is dense in this ideal, so it's certainly satisfactory to understand what happens in the subalgebra. Here's the formula. Suppose you now want to calculate the trace of f. This trace that we're discussing, evaluate the function of the identity. So what the formula is I'll go on the board. It's like this formula up here. It's before, actually the formula before this one, before we invoke the final trick involving the Parabolic measure, we had a formula back in a different context for a trace like this, and it had the following sort. It involved an integral of a Fourier transform. Now, the Fourier, the natural Fourier transform goes between functions on T and functions on T hat, which is a discrete set. So instead of an integral, there will be a sum. And then there's a certain numerical factor here. Which can be recognized combinatorially as very closely related to the numerical, to the machinery of Hammond-Weyl's character formula. I'll come back to that in just a moment. And then what I'm going to put is one of these, slightly change the notation here, one of these so-called orbital integrals Fourier transformed. That's it. And almost done. So f sub f, before you take its Fourier transform, is a function on T. And basically, it's this function here. But as it happens, it's convenient to take this quantity. Now, just like the compact groups, it turns out that this fellow here has a sort of holomorphic square root. And what you want to do is take one of them. I guess I wasn't specific enough, but I'm not sure which one the bar should go on. But I guess it doesn't matter.
Is that f or hat? What would you choose?
Everything
This is f sub f.
is, amazingly enough, everything is correct. Yeah. This is a function on the torus, a function on elements in the group G. This is a Fourier transform of that function. So its argument is a sort of abstract thing. It's a character, an n, if you like in the theory of Fourier series. This is Harishchandra's transform. There's a constant, which you can make go away by it's worth to say what these numerical factors are. Because it indicates, in fact, I think it's very important, indicates a strange connection between the group G and its compact form. Back many hours ago, when today started, many hours ago, we discussed how to relate any non-compact group to its so-called compact form. And the compact form now comes back into the picture at this late stage of the proceedings. But before we get to that, let me try and indicate the relevance for discrete series. If I have a discrete series representation, then it corresponds to some summand of the compact operators in this ideal. This whole ideal, as I mentioned this morning, is a direct sum over all compact representations, copies of the compact operators in the representation. And so you can build explicit elements in this compact, in this basic ideal, using matrix coefficient functions, as it happens, of discrete series representations. The way in which you go from vectors or operators down here to functions on G is through the explicit map is through taking matrix coefficient functions. And so you can build, each time you're down here, each time you have a compact representation, and therefore something definitely non-zero in this basic ideal, you can build a definite f, let's call it f sub pi. And you can calculate for this definite f sub pi what its trace is. The trace is this formal degree that we mentioned much earlier, the formal renormalized finite dimension of the infinite dimensional representation. And so that formal dimension is equal to blah, 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 one of these sums. And therefore, one of these numbers has to be non-zero. In fact, what happens is that exactly one of these numbers is non-zero, and all of the others are zero. And so there's a bijection between the discrete series, this is the rest of the theorem of Harris-Chandler, between the discrete series and the terms in this series, the terms for which this numerical factor is non-zero. Sometimes, as in Weil's character formula, the numerator, so to speak, this term here can be zero. So it's very, very interesting. This formula not only is reminiscent of what the formula we looked at before, it not only attaches invariance to discrete series representations, namely the phi's for which the corresponding term is non-zero, but that attachment of invariance classifies the representations for each discrete series. There's exactly one phi for which the corresponding term in this quantity here is non-zero. So that's the statement of the classification theorem. It's rather spectacular, and and now let me just try to explain what these numerical factors are, and then finally try to suggest a version of this which does not involve the sort of integration tricks that we talked about before, but directly involves Dirac operators at the moment. So this fellow here is a gigantic product of inner products. Like this. And now I just have to tell you what the various pieces are. So alpha here will be chosen to be a positive root of U. And U is the compact form of G. So you take G, you take its Lie algebra, which is K plus some P. You take P and you multiply it by the square root of -1, and that's now the Lie algebra of some compact group. And that compact group has a set of numerical invariants attached to it. So the alphas here are homomorphisms from the maximal torus into, sorry, the algebra from maximal torus, let's do it, into the maximal torus of the 1-by-1 unitary matrices, that's I times R. And what you're supposed to do is you're supposed to take U, which is a Lie algebra, and you're supposed to divide it by T. Now the quotient is just a vector space. But on the quotient, the group T acts by conjugation, and the same is true on the complexification. And that complexified representation breaks up as a direct sum of one-dimensional representations. That's always the case for abelian
representations of abelian compact groups. And those one-dimensional representations are, by definition, the roots. And each time alpha is, this is the infinitesimal formula, infinitesimal version of that one-dimensional character. It happens that each time you have a root minus that root, minus alpha is also a root, and there's a compatible way of choosing a system of positive roots. That's to say, out of each pair plus or minus alpha, you choose one of them. And that's what we've done here. And if you make different choices, it will affect this constant. So this is what it is. This is related to, let me draw a picture here. Here's an example. So this would be the picture for group SB4. This is a group with discrete series and has a two-dimensional maximal torus. And so this space of all possible phi's is a lattice in this space. I don't remember exactly what the spacing is. See? So the set of all possible phi's carried away is an integer lattice in this space. Now, what are the alphas? The alphas are vectors which are orthogonal to these so-called root hyperplanes. What I've drawn here are actually the kernels of the various alphas. So if you happen to have a dot which aligns on one of these walls, then there'll be an orthogonality here, and you just get 0. So this quantity is not all 0. And the ones that actually correspond to the discrete series are the ones not on any of these hyperplanes. Okay, but now I need to, yes, great. And so that's what this thing is, and the wait, I'm not going to say any more. Just to give you a sense of what's going on here. These numerical terms are of this general type, and the reason I mention all of this is that when you calculate the dimension of representations of compact groups using Weil's character formula, you take Weil's character formula and you plug in the identity for the character to get the dimension of the representation. The dimension is always given as a quotient, and this is the numerator. This is the numerator. So there's an interesting relationship with the compact form of G. And now let me, in the remaining few minutes, try to. So I shan't attempt to discuss the proof of this formula at all. It's a lot like the formula that we were discussing before, but it's more complicated. And the reason it's more complicated is that we're integrating here not over a vector space, but just over a bit of a vector space. And we're dealing with a formula here which is not true, not correct for any function f. It's only correct for those functions f which lie in this basic ideal. So there are more complicated aspects to this formula. But the same general ideas, same general principles apply. In this formula, the final version still involves a Fourier transform, and that's related to the fact that there is no n to do this final Fourier transform trick with. Okay. As I say, I'd like to just write down a formula. I know this formula is correct because this is a correct formula, but it would be very interesting to obtain a direct proof of that. First of all, if f is in the basic ideal, then according to the basic theorem, f acts as a compact operator on each one of these k isotypical components of G. The kernel, the integral kernel representing the operator, let's assume again we're in this dense subideal. Assume mine in just a moment. this space is the L2 sections of some vector bundle over G mod K, and so the kernel K of xy is actually defined on G mod K times G mod K. And the way you get such a function on G mod K is a formula similar to the one we had before. You take F, space here. You take F, and you just take G1, K, G2 inverse, and you integrate it over K, but that can't be right as it stands because I don't have sigma involved. And so what you have to add into this formula to make it a true summing is sigma of K. Sigma of K is a matrix. It's a unitary operator. But then again, this kernel is supposed to map sections of a certain vector bundle to sections of the vector bundle again. So the individual values of this kernel should be matrices, not scalars. And so the trace is the integral over G, the integral over K, of the trace of sigma, which is the character, okay, and F. It looks a lot like the integrals that we had non-material. You can still hear the integrals. Except it's K, not T, but that's not a big deal. We can continue. In this formula, we're integrating over K, but every integral over K can be interpreted as an integral over G mod T times T by the original Weyl integral formula. So you can get rid of K here at the expense of using the Weyl integral formula. And what you get now is an integral over G, an integral over G mod T, but sorry, K mod T, but the K mod T integral cancels off against the G integral. It's just really just an integral over T here. And what we're supposed to do is pi T. But now that you pay a price by going from K to T, and the price you pay is the Jacobian that appears in the Weyl integral formula. So the trace is nothing more than this quantity here. But remember that in Weyl's character formula, the character has a denominator, and the denominator is exactly the square root of delta of T. So what you get here is just some alternation of phi, the numerator, T times the square root here. We're supposed to be calculating trace here. Should have taken G1 equal to G2. So that's the kernel of traces. You integrate along the diagonal. Apologies. That's exactly what we had over here. So in other words, the terms in this formula are actually the traces of operators. told a sort of lie. To do bookkeeping with these Jacobian factors, what you find is that the right thing to start with is not the original representation sigma, but the original representation tensored with S, the vector space which appears in the definition of the Dirac operator. So the lemma comes out of it. It's not a theorem, it's just a, it looks like an index theorem, but it's just a direct calculation. These terms, F maps of F phi, Harris-Chandler's formula. Are traces, honest to goodness traces. So what I'm going to do is I'm going to take F and think of it as an operator on a certain space. And just for fun, I'm going to multiply, as people do, by the e to the minus Dirac squared. You don't actually need this. You could set t equal to 0. This is a true formula. But this is lambda regular representation. So this is acting the L2 space in G mod K, coefficients in the vector bundle. And this should be one of these graded traces. It's not an index theorem. It's a direct analytic, just a direct check that such a formula is correct. The orbital integrals, as they're called, the terms in Harris-Chandler's formula, have another life, and the traces associated to Dirac operators in this way. And so I'm not going to keep you any longer, so let me just say that Harris-Chandler's formula has an interpretation. Formula relating this interesting von Neumann trace evaluation of the identity to ordinary traces in, let's say, Dirac index. And it would be very nice to obtain a direct analytical proof of this, because then you wouldn't have to worry about Harris-Chandler's formula and all of its details. If you add up these Dirac operators with all of the correct multiplicities which appeared in Harris-Chandler's formula, these fellows here, what you find formally is you get the Dirac operator in G, you get the Dirac operator on G mod K acting on the following infinite, with coefficients in the following infinite dimensional vector space. Namely, you take the space U modulo K, where U is the compact form of K, and you build the Durham operator on U modulo K. So here's the formula. It says trace G is equal to the usual operator trace, again, of lambda times. Now I'll take e to the minus t, and what I'm going to put here is the Durham operator squared. The last thing I'll write is d is the Durham on u. The index here is known to be the size of the value for u. In particular, not zero. Harris-Chandler's formula is equivalent to this statement, that this funny von Neumann trace can be written as a strange thing. This is the trace of an operator on the following rather large space. We'll take L2 of G, mod K, with values in the space of L2 forms on U mod K is here. If I just put G mod K here, then I should just put U. And lambda means different. Okay, so here's an exotic von Neumann trace, here's an ordinary operator trace. Both sides are well-defined and completely analytic, and if you could show they were the same, which is confusingly difficult to do because on this space, the way this drama is working is acting as a transversely elliptic operator. These are the exterior of the horizontal forms, not all forms. But if you could show that these two things are the same, after all, they're both analytically defined, they're equal, they're known to be equal, so you just have to show them. Then you can have Harris-Chandler's formula, and that would take you a long way towards the classification of the discrete series. That's where I am right now. I don't know how to do that final step. Good. I think it's definitely time to stop. So thank you so much for your patience today.
Thank you very much for stimulating, passionate lecture. Any question or comments?
Maybe the final, let's give the dimensional space, which is like a triple bundle over G over K. Like,
Yeah, let me say it more clearly. You take, so U, the group U, which is a compact group, let's take the simplest case where the group G is SL2R. Then U is SU2, and inside of SU2 is SO2. And here's what I want to do. I want to take the Durand operator on SU2 divided by SO2, that's the complex projective line. I want to take the Durand operator, and I want to lift it to an operator on this principal circle bundle over the projective line, over CP1, which is the 3-sphere, which is U. Okay? And so I want to lift it just as a transversely elliptic operator. And so what D means here is the operator associated to the Durand complex upstairs on horizontal forms. So it's a transversely elliptic rather than elliptic operator, and this trace does not obviously exist. It only exists if F lies in the basic ideal that I was describing, not for an arbitrary F. So it's a little bit delicate what's going on. But this makes sense some of the time, for some Fs, and Fs in the basic ideal. Of course, this makes sense all of the time. If F is in the basic ideal, these two quantities should be the same, up to some numerical factor, of course. And, well, I know they are the same, thanks to Harris-Chandler's formula. But I would like a direct argument to calculate that this trace is equal to this trace, just by changing the basis or something. And I don't have that. Yeah, and what makes it tricky is that it's a transversely elliptic operator, which appears not an elliptic operator.
So the proof of this lemma is somehow independent from the proof of Harris-Chandler.
Yeah, this is just a check of definitions. The fact that these can be identified with operator traces is, you go line by line to see that all the definitions match up. And so you can interpret Harris-Chandler's formula as exactly this assertion. Right, so this complicated trace you can decompose into an infinite sum of simple traces like that. That's elementary. Hard thing is this quantity sum. So this, if you like, is a theorem of Harris-Chandler, but it should be a direct theorem, direct computation of me.
So if you let t to the infinity, would you expect this equality or
Yeah,
relative?
that's exactly what I want to do. I want to calculate, actually the best thing to do is let t go to 0. When t goes to 0, the explicit analytic form for this should converge to the explicit analytic form for this. And but you can see that it's sort of correct. As t goes to 0, the information regarding f that contributes to this formula, this quantity, is information contained in any arbitrarily small neighborhood identity. So you know it's something like this, but I don't know it's exactly this.
Other question? Okay, so once more, thank you, speaker.